Could a golden eagle spot a rabbit from 3 kilometers away if it couldn't see the individual hairs on a creature the size of a bread loaf? In the thin air of the Scottish Highlands, researcher Graham Martin spent years documenting this biological sensor suite. He noted that the bird's eye is physically impossible by human standards. If our eyes were proportional to an eagle's, they would be the size of grapefruits and weigh more than our entire brain. The bird's skull serves as a housing unit for 2 massive, high-definition cameras, leaving barely enough room for the gray matter required to process the incoming flood of data. In 2012, Martin published findings in his work, Through Birds' Eyes, detailing how raptors perceive a world fundamentally different from our own. While a human eye sees about 24 frames per second, a hunting eagle processes visual information at nearly double that rate to prevent what pilots call motion blur. When the bird tilts its head at a 45-degree angle, it is switching between 2 different focal points. These predators possess a dual fovea system, allowing them to maintain a sharp, magnified focus on a distant target while simultaneously tracking the horizon for threats. It is a biological heads-up display that never lags, even during a high-speed descent. The physics of this vision relies on a specialized structure called the pecten. This comb-like crown of blood vessels inside the eye reduces shadows and prevents light from scattering. In the late 20th century, Tom Cade and other ornithologists at Cornell University observed how this anatomy allowed falcons to track prey against the blinding glare of a midday sun. The bird does not squint or lose the target in the wash of white light. Instead, the eagle's eye acts like a polarized lens, cutting through atmospheric haze and reflections on the water to reveal the exact position of a trout or a hare. But the real mystery lies in the processing speed. During a hunt, an eagle's brain must calculate wind speed, trajectory, and the erratic movements of a fleeing animal in real time. In the 1980s, field observations recorded eagles navigating through dense forest canopies at 60 miles per hour without clipping a single wingtip. This requires a neural refresh rate that science is still struggling to map. A human pilot would experience a total system crash trying to navigate those gaps at that velocity. The eagle treats the obstacle course of branches like a slow-motion playback. The sensory suite extends beyond just clarity. Raptors can see into the ultraviolet spectrum, a reality Graham Martin highlighted as a key to their survival. To an eagle, a field of grass is a map of chemical signals rather than a simple green pasture. Small rodents leave urine trails that reflect ultraviolet light, glowing like neon signs against the dull earth. The bird follows a glowing highway that leads directly to the nest instead of looking for the mouse itself. It is a predatory hack to see the invisible, turning the mundane landscape into a high-contrast targeting grid. In 2005, a pilot and falconer named Ken Franklin decided to measure the limits of this precision during a vertical dive. He took his trained peregrine falcon, frightful up to 12,000 feet in a Cessna. Franklin then skydived alongside the bird, wearing a specialized GPS unit while the falcon carried a matching device. The data returned was staggering. During the stoop, the falcon reached a top speed of 389 kilometers per hour. At that velocity, the air pressure alone should have collapsed the bird's lungs. Instead, a series of small, bony tubercles in the nostrils acted as baffles, slowing the air down so the bird could breathe while falling at a third of the speed of sound. This brings us to the most difficult question in avian biology. As a bird approaches these terminal velocities, The physical stress on the skeleton becomes immense. Every turn exerts multiple G-forces on a frame that must remain light enough to fly. In 1998, biologist Vance Tucker at Duke University developed aerodynamic models to understand how a raptor's feathers stay attached under such pressure. He found that the microscopic barbs on the feathers act like Velcro, locking together to create a rigid, seamless armor. If a single feather were to fail or flutter, the resulting turbulence would tear the wing apart. The sheer scale of these aerial hunters has varied wildly across deep time. While the golden eagle is a master of the modern sky, the fossil record contains hints of giants that seem to break the laws of aerodynamics entirely. In museum basements from South Carolina to Argentina, there are fragments of wings that span the width of a two-car garage. These were biological anomalies that shouldn't have been able to get off the ground. The weight of their bones alone suggests a creature that would be too heavy to generate lift. Yet the evidence shows they ruled the oceans for millions of years. We have spent decades trying to reconcile the weight of a predator with the requirements of flight. Modern raptors use hollow bones and air sacs to stay light, but there is a limit to how large a bird can grow before the bone becomes too brittle to support the muscle. Yet something in the ancient past bypassed this restriction. The index has flagged a specific discovery that challenges our entire understanding of how a giant hunter stays airborne. It involves a skeleton found in a location that was once a shallow sea, belonging to a creature that shouldn't have been able to fly, let alone hunt. The archive now turns to a specific 2014 skeletal analysis of a creature with a wingspan twice the size of a royal albatross. We will examine the weight-to-strength ratio that allowed this giant to defy the laws of avian physics and maintain a predatory grip on the prehistoric world. The data suggests an anatomical shortcut that allowed for massive size without the penalty of weight. This record, filed under the impossible engineering of the sky, is essential to understanding the limits of biology. What the index concludes: why does every nature textbook and trivia log treat the peregrine falcon's speed as an absolute, unquestioned truth? In February 2005, pilot and skydiver Ken Franklin took Frightful, his trained falcon, to an altitude of 17,000 feet. Franklin stepped out of the plane, and the bird followed. As they dropped toward the earth in a vertical stoop, a GPS device on the bird recorded a top speed of 389 kilometers per hour, exactly 242 miles per hour. At that velocity, air stops behaving like a gas and hits like a solid wall. The physics of this dive should be lethal. Standard biology suggests a creature moving at nearly 400 kilometers per hour would suffer total respiratory collapse. Fast-moving air creates a high-pressure ram effect that acts as a death sentence for living lungs. This pressure should inflate the bird like a balloon until the delicate air sacs burst. Even if the lungs held, the bird would suffocate because the velocity creates a vacuum at the back of the throat, making it impossible to draw a breath. Yet the peregrine does not explode or pass out from hypoxia. It tracks its prey with cold-blooded precision. The official explanation for this engineering miracle points to two tiny bumps inside the falcon's nostrils called tubercles. For decades, scientists agreed these bony spirals act as baffles to break up supersonic airflow, slowing it down to a manageable pressure. Human engineers eventually adopted this biological design. If you stand near the intake of a modern jet engine, you will see a metal cone in the center that looks hauntingly similar to the anatomy of a falcon's nose. The bird is effectively a living jet engine. However, the math does not hold up. In 1998, Vance Tucker of Duke University's Department of Biology put this theory to a rigorous test. He built an aerodynamic model to calculate the maximum dive and pull-out speeds for the species, looking for the hard limits of avian physiology. Tucker found a glaring discrepancy. While the tubercles manage airflow, they cannot account for the massive G-forces a falcon sustains. When a bird levels out from a 389 km/h dive, it experiences forces up to 25 G. A trained fighter pilot will black out at 9 G. If the falcon were merely a fast glider with a clever nose, it would die the moment it tried to strike. The pressure on the eyes alone is enough to cause permanent retinal detachment. To combat this, the bird uses a nictitating membrane, a third eyelid that sweeps across the eye like a high-speed shutter. It clears debris and keeps the surface moist, but it cannot reinforce the skull against 25 G. A hidden mechanical strength in the raptor's frame defies the standard hollow bone narrative. The falcon is built with the reinforced density of a projectile. We are told these birds are the ultimate hunters because they have mastered the physics of the fall. But speed is a double-edged sword. At 389 km/h, a single mistimed wing beat or a slight gust of wind would result in mid-air disintegration. The bird's feathers are stiff, short and packed with a density that feels more like plastic than plumage. Tom Cade, who founded the Peregrine Fund in 1970, spent years documenting how these birds recovered from the brink of extinction. He noted their resilience, yet even his records struggled to explain how an organism survives the heat and friction generated by these terminal velocity runs. There is another hole in the perfect hunter narrative. If speed is the ultimate weapon, the peregrine should be the most successful predator in every environment. It isn't. In the pitch-black woods of the Pacific Northwest or the forests of Europe, speed is a liability. You cannot stoop at 242 mph through a canopy of ancient Douglas firs. In 1971, Roger Payne of Cornell University proved that some raptors don't need to see their prey at all. He demonstrated that barn owls could strike a target in total darkness using nothing but sound. This discovery shifted the focus from speed to silence. The world assumed the owl was the stealthy counterpart to the falcon's power. Researchers like Justin Jaworski and Christopher Clark spent years analyzing the aeroacoustics of owl wings, finding specialized serrations on the leading edges that break up the sound of moving air. By 2013, the consensus was reached. The owl is silent and the falcon is fast. We filed the birds of prey into neat categories. One uses the hammer of velocity, while the other uses the cloak of silence. The data eventually moved in a strange direction. In 2020, Christopher Clark published a reassessment that shook the ornithological community. He proved that owl flight is not silent. It produces a distinct acoustic signature that simply falls outside the audible range of the rodents they hunt. It is a frequency heist. This realization forced researchers to look back at the peregrine falcon and the golden eagle. If we were wrong about the owl, what were we missing about the falcon? The answer was in the bones. When scientists re-examined the skeletal remains of history's most successful aerial hunters, they found an anomaly in the jaw structure of the largest raptors to ever fly. This feature suggests their hunting method had nothing to do with speed or sound, but a third, much stranger physical property. The record shows that, as these birds grew larger, their bodies began to mimic a biological structure usually reserved for deep-sea predators. This discovery leads to a record filed under the impossible, a bird with a wingspan of 24 feet that carried a secret inside its beak. What the index concludes, the peregrine's speed is not a biological peak, but a specialized deviation from a much older, more lethal aerial blueprint. Can a bird truly disappear while moving through the sky? At 10 feet, the flight of an owl produces 0 decibels of sound. There is no whisper or rustle, only a total acoustic void. During a 2017 laboratory test, researchers positioned high-sensitivity microphones along a flight path and released a barn owl into the darkness. The equipment was calibrated to detect the faint hum of a cooling fan or the brush of a sleeve. Yet as the bird passed inches from the sensors, the needle remained flat. It appeared as if the air itself refused to vibrate. For decades, biologists attributed this to the soft, velvet-like down covering the feathers, assuming it functioned like acoustic foam in a recording studio. However, the index has logged a discovery suggesting the owl is engineered for silence at a structural level that challenges our understanding of fluid dynamics. Justin Jaworski at Lehigh University examined the leading edge of the wing in 2013. He discovered a microscopic row of stiff, comb-like bristles. These are rigid structures, spaced with mathematical precision to break up the air before it can form a noisy vortex. Imagine a serrated knife slicing through silk rather than a blunt blade tearing it. The bristles force the air into laminar flow, preventing the turbulent whoosh that alerts a rodent to a predator's approach. Jaworski's aeroacoustic model revealed that the owl's wing is essentially a biological stealth fighter, utilizing geometry rather than just padding to vanish from the auditory spectrum. This revelation caught the attention of engineers trying to silence wind turbines and submarine propellers. Roger Payne proved the stakes of this silence in 1971 at Cornell University. He placed a barn owl in a room of absolute, suffocating darkness with 0 light, not even infrared. He then scattered dry leaves on the floor and released a mouse. The owl did not just fly. It struck with total precision. It didn't need to see the mouse to kill it. Payne realized the owl was triangulating the rustle of the prey with an error margin of less than 1 degree. The bird's facial disc, that heart-shaped mask of feathers, acts as a parabolic sound collector, funneling noise into ears placed asymmetrically on the skull. One ear sits higher than the other. This offset allows the owl to map sound in 3 dimensions, calculating both elevation and distance simultaneously. Silence is the primary requirement for this biological radar to function. If the owl's own wings made noise, it would deafen itself to the heartbeat of its prey. In 2020, Christopher Clark at the University of California took this investigation into new territory. He discovered that while the owl is silent to a human or a mouse, it isn't truly silent to the physics of the atmosphere. The wing beats produce sound in a frequency range that sits outside the biological hardware of most terrestrial mammals. It is a form of frequency-shifting camouflage. The owl is not hiding from the air, but is instead operating in a narrow, invisible acoustic window that the rest of the forest cannot perceive. This brings us to a documented anomaly from a 2015 field study in the Pacific Northwest. Researchers were using specialized sonar arrays to track nocturnal hunters in a dense canopy. They expected to see the sound signatures of bats and the occasional heavy wing beat of a hawk. Instead, the sonar logs recorded ghost movements. The sensors would trigger, indicating a mass was moving through the airspace at 30 miles per hour, but the acoustic return was non-existent. The technicians checked the power supply and the cable shielding to rule out a hardware malfunction. They found nothing wrong with the machines. Something was moving through the woods that was physically present but acoustically absent, even to military-grade sonar. The team recovered a single feather from a low-hanging branch near the sensor array. It belonged to a great gray owl, the largest owl species by length in North America. When they brought the feather to a lab for microscopic analysis, they found a detail the textbooks had missed. The combs on the leading edge were not just hair-like structures. They were coated in a unique, waxy protein that seemed to absorb moisture. This is critical because humidity changes the density of air, and therefore the speed and volume of sound. By regulating the microclimate around its own wing, the owl was effectively stabilizing the medium it moved through, ensuring its silence remained perfect regardless of the weather. The implications of this biological engineering are staggering. If a bird can manipulate the air to such a degree, we have to ask if our current understanding of avian evolution is complete. We see the owl as a bird that evolved to be quiet, but the data suggests it is a specialized instrument designed to exploit a loophole in the laws of physics. In the 1982 archive of Tom Cade, he noted that the hunting success rate of a barn owl in total darkness exceeded 80%. Compare that to a lion, which succeeds in 20% of its attempts. The owl isn't hunting, it is harvesting. It is an apex predator that has removed the variable of detection entirely from the equation of survival. However, the index has identified a recurring discrepancy in these records. While the silent flight mechanism is well documented in modern owls, there is a gap in the fossil record regarding when this stealth technology first appeared. Most raptors from the Eocene period show standard feather structures built for power and speed, not silence. Then suddenly, the specialized serrations appear in the record without a clear transitional form. It is as if the software for stealth flight was patched into the avian lineage overnight. This sudden leap in capability suggests that the pressures of the nocturnal environment forced a radical, almost impossible biological pivot. Consider the physics of the kill. A bird of prey must balance the weight of its weapons against the necessity of flight. To be fast, like the falcon, you need stiff, heavy feathers. To be silent, like the owl, you need light, porous structures. Evolution usually forces a trade-off where you can be the bullet or you can be the shadow. But the index has uncovered evidence of a lineage that attempted to be both. In the deep time records of the Miocene, there are hints of creatures that defied this binary. These were birds with wingspans that should have been physically impossible to move silently, yet their skeletal remains show the same parabolic ear structures found in the barn owl. We are left with a chilling realization. If the owl achieved perfect silence through microscopic geometry, what other adaptations have we missed because they are too small or too strange to fit our models? The falcon dominates the day with raw kinetic energy, and the owl dominates the night with acoustic erasure. But there is a third category of hunter mentioned in the margins of early 20th century expedition logs. A bird that doesn't use speed or silence, but something else entirely to secure its prey. If the secret wasn't in how they moved, but in what they were moving with, the entire history of the sky changes. What if the most effective weapon in the air wasn't a claw or a beak, but a structural deception built directly into the bone? What the index concludes: the owl does not fly through the air. It manipulates the air into a state of total compliance, proving that evolution prioritizes the erasure of evidence over the exertion of force. How does a 5-inch talon compare to the weaponry of the world's most feared land predators? The harpy eagle possesses claws longer than those of a grizzly bear, a measurement that translates directly into mechanical devastation. When this raptor closes its foot, it exerts over 500 pounds of pressure per square inch. This force snaps the spine of a sloth or crushes a primate's skull instantly. In the humid Amazonian canopy, a successful strike produces no scream, only the sickening crack of bone under hydraulic tension. The harpy eagle remains the undisputed heavyweight champion of the modern sky, a 5-foot-wide predator navigating a world of vertical obstacles and suffocating heat. Biologists like Graham Martin have spent decades investigating how such a heavy creature navigates a labyrinth of branches at high speed without shattering its wings. In his 2012 synthesis, Martin noted that the harpy ignores the soaring mechanics used by the red-tailed hawk. It operates instead like a tactical interceptor. Short, broad wings allow for explosive bursts of speed in tight spaces, while massive legs act as shock absorbers for high-velocity impacts. When the eagle strikes, it anchors itself. It uses its body weight to swing beneath a branch, employing gravity to increase the torque of its grip. The power of the harpy eagle forces a reconsideration of the limitations of avian biology. If a 20-pound bird kills creatures half its own weight, the physics of the past become terrifying. Museum archives and fossil catalogs contain records of birds from the last 10,000 years that dwarf the harpy. These were active predators with skeletal structures designed for extreme loads. The Haast's eagle of New Zealand, for example, possessed a pelvis so wide and legs so thick that researchers initially mistook the remains for those of a flightless bird. It specialized in taking down the moa, a creature 10 times its size. Even the Haast's eagle follows the rules of traditional biology, using a beak for tearing and talons for gripping. Records in the Deep Index, however, reveal anomalies that break these fundamental rules. In the mid-20th century, paleontologists uncovered remains of the Pelagornithids, the bony-toothed birds. These creatures patrolled the oceans with 24-foot wingspans, twice the size of a wandering albatross. For years, the mystery centered on how they fueled such a massive frame. A bird of that scale requires immense caloric intake, yet the energy cost of carrying heavy hunting tools like thick talons or serrated teeth would usually make flight impossible. Engineering in the sky took a turn into the unexplained during a 2014 study at the Charleston Museum. Researchers analyzing a specimen of Pelagornis sandersi realized the bird solved the weight-to-power ratio by defying standard evolutionary logic. The creature appeared to have a mouth full of sharp, needle-like teeth for snatching slippery fish. But birds lost their teeth millions of years ago to save weight. The fossil showed something different. These were not teeth, but a biological workaround that allowed a giant to rule the sky without the heavy baggage of its ancestors. The secret lay in the jawbone. Instead of growing teeth from sockets, which requires dense bone and heavy enamel. The Pelagornis evolved pseudo-teeth. These hollow, jagged protrusions of the mandible were covered in a thin layer of keratin. This lightweight serrated edge grew directly from the frame of the face. It allowed the bird to maintain a 24-foot wingspan while possessing the gripping power of a shark. By turning its own skeleton into a weapon, the bird bypassed the metabolic cost of dental development. The existence of these pseudo-teeth raises a troubling question for the timeline of avian development. If these structures were so efficient, why did they vanish? The fossil record shows these giant gliders dominated the planet for over 50 million years, surviving climate shifts that wiped out thousands of other species. They were the ultimate aerial platform, refined by tens of millions of years of selection. Then they simply ceased to exist. We often blame extinction on a lack of adaptation, but the Pelagornithids were the most adapted flyers to ever live. Their disappearance suggests a shift in the environment so radical that even a perfect design failed. We see the remnants of this specialized power in the modern Harpy eagle. The Harpy's grip is a concentrated version of that ancient mechanical dominance, though it is a specialist of the forest, while the Pelagornis ruled the open wind. Modern physics shows a trend towards smaller, faster, and more efficient hunters. The giants are gone, leaving behind only the most extreme versions of their weaponry. We are left to wonder if the limits of flight are dictated by the air itself, or if there is a ceiling to how large a predator can become before it collapses under its own success. The grip of the Harpy is the strongest in the modern world, but it is a shadow of what once patrolled the horizon. Science can explain the pressure of the talon and the lift of the wing. We can calculate the foot-pounds of force and the drag coefficients of the feathers. But the records in the archive point to a period where the rules were different. There was a time when the sky supported creatures that should have been physically impossible. They thrived in a world that demanded more energy than the modern Earth seems able to provide. If the Pelagornis used its own jawbone to mimic teeth, it suggests that the drive to hunt forces biology to find the most bizarre, efficient shortcuts imaginable. The bony-toothed birds were a masterpiece of compromise rather than a failure of evolution. As we examine the final specimens of these giants, a new anomaly appears in the data. It is not a question of how they flew or how they killed. It is a question of what they were actually eating. The pseudo-teeth of the Pelagornis were designed for something much larger and more elusive than fish. What were these 24-foot giants hunting in the open ocean that required a serrated jaw? The evolution of avian weaponry proves that nature will sacrifice the very structure of a skeleton to maintain the lethality of the hunt. Why would a creature with a mouth full of jagged spikes ever need to evolve such a nightmare? In 1983, construction crews building a new terminal at the Charleston International Airport struck something hard within the Chandler Bridge Formation. The air smelled of damp silt and diesel exhaust. A single worker knelt in the mud, clearing away gray sediment to reveal a narrow, elongated beak nearly 2 feet long. It looked like a relic from a fever dream, a bird's head armed with rows of needle-sharp protrusions. This was Pelagornis sandersi. It existed 25 million years ago, patrolling the Oligocene skies over what is now the American South. The sheer scale of the find defied the established limits of avian physics. A bird's wing is a compromise between lift and structural integrity. In a quiet museum basement, Dr. Daniel K. Sepka lifted a single humerus from a padded drawer. The bone was thin, light, and almost the length of a human arm. When Dr. Daniel K. Sepka input the measurements into a flight performance model in 2014, the results were staggering. Pelagornis sandersi possessed a wingspan of 24 feet. That is twice the size of a wandering albatross, the largest flying bird alive today. It is wider than a standard shipping container. The physics suggested a creature that could not possibly take off by flapping. Yet the 1983 discovery proved it dominated the prehistoric oceans for millions of years. The mystery deepened when researchers looked at the creature's mouth. True teeth are heavy. They require deep sockets, dense enamel, and a massive jaw to anchor them. This is weight that grounded most birds long before the dinosaurs vanished. But this creature had found a loophole in the laws of biology. The spikes lining its beak were hollow. They were not separate structures, but direct extensions of the jawbone itself. They were pseudo-teeth. This meant Pelagornis could snatch slippery, soft-bodied prey from the ocean surface without the aerodynamic penalty of a heavy skull. It was a specialized killing machine designed for a world of endless flight. How does a creature with the wingspan of a small Cessna get into the air? The fossil site in South Carolina sat near an ancient coastline where the wind never truly stopped. Calculations by Dr. Daniel K. Sepka and his colleagues suggested Pelagornis was a master of dynamic soaring. It didn't flap its wings to stay aloft. Instead, it harvested the energy of the wind gradients above the waves. Like a high-performance glider, it could travel hundreds of miles without a single wing beat. The smell of salt spray and the sound of rushing air would have been its constant companions. It lived a life almost entirely detached from the land. The sheer size of Pelagornis sandersi forces a reassessment of what we know about avian limits. For decades, biologists believed that a 20-foot wingspan was the absolute maximum for a feathered creature before its wings would simply buckle under the stress of gravity. Pelagornis pushed 4 feet past that limit. The bones found at the airport terminal were incredibly thin, some less than a millimeter thick in places. It was a biological miracle of lightweight engineering. Yet this fragile giant survived an era of massive climate shifts and shifting tectonic plates, thriving where smaller, more robust birds failed. Consider the perspective of the prey. An ancient squid surfacing at dusk would see a shadow block out the stars. No sound would herald the approach. The bird's wings were so long and narrow they functioned like blades, cutting through the air with minimal turbulence. The pseudo-teeth were angled backward. Once a fish was caught in that serrated grip, there was no escape. The mechanics were perfect. The design was efficient. So efficient, in fact, that variations of these bony-toothed birds persisted for over 50 million years, a reign far longer than that of modern raptors. In 2014, the findings were published in the Proceedings of the National Academy of Sciences, officially logging Pelagornis sandersi as the largest flying bird ever discovered. The report detailed how its long, slender wings were optimized for gliding over the open ocean, much like the modern frigate bird, but on a terrifying scale. It was the undisputed king of the sky, a creature that turned the Charleston coastline into a hunting ground. It seemed invulnerable, a peak predator that had solved the weight-to-power ratio that limits every other bird in the sky. But the record contains a glaring inconsistency. If Pelagornis sandersi was the ultimate aerial design, why did it vanish? The Oligocene gave way to the Miocene, and the oceans remained full of life. The winds still blew. Yet these giants disappeared from the fossil record, leaving only their smaller, toothless relatives behind. The heavy-boned penguins and the agile gulls survived, while the master of the 24-foot wingspan faded into the silt of South Carolina. The very specialization that allowed it to grow so large may have become its death sentence when the environment shifted. The discovery at the airport was just the beginning of a larger investigation into the limits of flight. We know that the peregrine falcon uses speed and the golden eagle uses vision, but Pelagornis Sandersi used sheer scale. It proved that nature could build a giant without the weight of a monster. Every bone in its body was a testament to the extreme measures life will take to conquer the air. But as researchers mapped the final flight paths of these bony-toothed giants, they realized the spikes in the jaw were hiding a much stranger secret than just weight reduction. The spikes were not just for hunting. Under high magnification analysis, the growth rings within the pseudo-teeth revealed a pattern that looked less like a predator's weapon and more like a sensory organ. If these jagged protrusions weren't just for gripping fish, what were they actually measuring? The team looked back at the South Carolina site, realizing the sediment layers held one more anomaly they had overlooked. The question wasn't just how Pelagornis flew, but what it was searching for in the deep water that required such a bizarre anatomical sacrifice. What the index concludes: the Pelagornis Sandersi record confirms that biological limits on size are not fixed, but are constantly negotiated by the environment, leaving us to wonder what other giants are currently hidden by the scale of the sea. Why did the physics of a prehistoric bird crash a high-end computer model? At Duke University, Vance Tucker and his team of biologists stared at a digital rendering of Pelagornis Sandersi, a creature with a 24-foot wingspan that once patrolled the skies of South Carolina. The data was clear: the bird was too heavy. According to every known law of avian flight, a bird of this mass could not generate enough lift by flapping its wings to leave the surface of the ocean. It was a biological brick. Yet the fossil record proved this creature lived for millions of years, traveling thousands of miles across open water without a single place to land. The scientists realized they weren't looking at a bird that flew in the traditional sense. They were looking at a living glider that had bypassed the need for muscle power entirely. This anomaly forced researchers to look closer at the living descendants of these giants. In the late 1990s, Vance Tucker transitioned from digital models to real-world observation, studying how modern raptors manage the grueling energy demands of long-distance travel. He found that eagles and hawks possess a specific anatomical lock in their shoulder joints. This specialized tendon and bone arrangement allows the wing to remain fully extended and rigid without a single spark of muscular effort. When an eagle catches a thermal, it isn't holding its wings out. It has clicked them into place, turning its entire body into a static aerodynamic tool. This discovery changed the narrative of the hunt. The most dangerous predators in the sky aren't the ones working the hardest. They are the ones who have mastered the art of doing nothing. The secret to this effortless suspension lies in the coracoid bone, a structural anchor that acts like a strut in a high-performance aircraft. In 2012, Graham Martin at the University of Birmingham noted that this skeletal rigidity is what allows a bird of prey to maintain a steady gaze while moving through turbulent air. If the wings were constantly vibrating or flapping, the bird's vision, the very thing that makes it a predator, would be a blurred mess. By locking the skeleton, the bird creates a stable platform for its eyes. It is the same principle used in modern tank barrels that remain level while the vehicle bounces over rough terrain. The bird becomes a floating camera, disconnected from the chaos of the wind. But the Duke University models revealed a darker side to this efficiency. While the lock allowed for incredible endurance, it created a terrifying problem for takeoff and maneuverability. If a bird is designed strictly for gliding, it becomes a prisoner of the weather. Pelagornis Record could spend years at sea, but if the wind died, it would drown. It could not flap its way out of a calm. This led researchers to a startling realization about the evolution of flight. The most successful hunters in Earth's history were also the most vulnerable. They lived on a knife's edge, where a single change in air pressure could mean the end of an entire lineage. The perfect wing was also a potential death trap. This vulnerability is mirrored in the flight of the peregrine falcon. While Ken Franklin's 2005 GPS data proved the falcon could hit 242 miles per hour, the physics of pulling out of that dive are nearly impossible. Vance Tucker's calculations showed that at those speeds, the G-forces exerted on the bird's frame should theoretically snap its wings off. The falcon isn't just fast, it is operating at the absolute structural limit of what bone and feather can withstand. To survive the hunt, the falcon has to utilize a rhythmic tuck that changes its center of gravity in milliseconds. 1 inch of error in the shoulder lock, one mistimed twitch of a primary feather, and the bird disintegrates before it even touches its prey. In 1982, Tom Cade, the founder of the Peregrine Fund, documented how these birds utilize slope soaring, a technique where they deflect off the wind, hitting a cliff face to gain altitude without flapping. It is a calculation of pure geometry. The birds are reading the invisible contours of the air, seeing the wind not as a gas, but as a solid landscape they can climb. This shifted the focus of the 1982 study from the bird's muscles to its brain. We realized we weren't just documenting animals. We were documenting biological computers that could solve complex fluid dynamic equations in real time. They aren't just flying through the atmosphere, they are manipulating it. However, a massive discrepancy remained in the data. If these birds are so perfectly tuned to the physics of the sky, why did the largest of them vanish? The disappearance of the giant gliders like Pelagornis wasn't caused by a lack of prey or a change in temperature. It was a failure of the wind itself. When the global climate shifted and the massive trade winds of the Miocene began to stutter, the birds with the locked shoulders found themselves grounded. A 24-foot wing is an asset in a gale, but a liability in a breeze. They were too specialized to survive a world that moved slower than they did. This brings us to the most unsettling part of the record. Modern eagles and vultures still carry this ancient lock in their shoulders. They are built for a world of high-energy thermals and consistent winds. But as urban heat islands and shifting weather patterns alter the way air moves over our continents, we are seeing a strange phenomenon in the tracking data. Birds are being found exhausted in places they shouldn't be, grounded in the middle of forests or flat plains, unable to find the elevator they need to get back into the sky. The very evolution that made them the masters of the sky has left them tethered to a system they cannot control. The Duke University team eventually reran the Pelagornis simulation with a new variable. What if the bird didn't take off from the water? What if it needed a specific type of wave, a rogue height to act as a catapult. The math finally worked, but it revealed a terrifying truth. These creatures didn't just hunt in the storm. They were part of the storm. They required the most violent conditions on Earth just to function. Without the chaos of the open ocean, the most magnificent wingspan in history was useless. It was a creature that lived in the eye of a needle, dependent on the most volatile forces in nature. So the physics of the kill is not about strength. It is about the exploitation of a lock, a mechanical cheat code that allows a bird to stay in the air forever. But if the lock is the secret to their success, it also points to a missing piece of the puzzle. The fossilized skull from South Carolina, the one with the jagged spikes instead of teeth, shouldn't have been able to eat what the models suggested it was catching. The spikes were angled in a way that would shatter if they hit a fish at the speeds the bird was gliding. This leads us to the final entry in the record. If the wings were built for speed, but the mouth was built for something else, what exactly were these hunters pulling out of the water? Why did the serrations on the beak of Pelagornis sandersi look like teeth, yet lack the heavy roots of a predator? These were pseudo-teeth formed directly from the jawbone. This architecture allowed a bird with a 24-foot wingspan to snatch slippery prey without the weight of true dentition. Researchers sought this specific payoff when they first pulled the massive skull from the earth in South Carolina. The specimen had waited 25 million years to reveal a secret of biological engineering that redefined the limits of flight. In 2014, Dr. Daniel K. Sepka sat in a quiet room at the Bruce Museum. Weighing the fossilized fragments, he realized he held a masterwork of weight-to-strength ratios. The creature had achieved the lethality of a shark while remaining light as a feather. Remember the mystery of the Charleston International Airport. In 1983, construction crews uncovered a skull so large it looked like it belonged to a dragon. It was a giant that dwarfed the Royal Albatross, the previous gold standard for aerial size. For decades, the math failed to add up. How could a creature with a wingspan twice the size of a modern glider stay aloft? The weight of a mouth full of teeth would have dragged the skull down, making the bird top-heavy and aerodynamically impossible. The answer lay in the bone density. Unlike the heavy, calcium-rich roots of a mammalian tooth, these spikes were hollow. They were extensions of the beak, grown like jagged mountain peaks from the jaw itself. The physics of the kill required a specific kind of violence. Pelagornis patrolled the prehistoric oceans, gliding for thousands of miles without flapping its wings. When it spotted a fish or a squid near the surface, it clamped down hard. True teeth required deep sockets and heavy muscle to keep from being ripped out by struggling prey. By integrating the teeth into the skeletal structure of the jaw, the bird eliminated the need for deep roots. This saved several pounds of weight at the very front of the body, where every gram counts for a flyer. It was a specialized adaptation that allowed a giant to defy the laws of avian physics. A single golden eagle can spot a rabbit from 3 kilometers away, a feat of optics that seems like magic. But Pelagornis had to solve the problem of scale. At 24 feet, a wing is no longer just a limb. It is a structural liability. In his 2014 analysis, published in the Proceedings of the National Academy of Sciences, K. Sepka used computer models to test the bird's glide ratio. The results were staggering. The bird was an ultra-efficient soaring machine. It could travel at speeds that would tear the feathers off a lesser animal. The mouth remained the focal point. Without those pseudo-teeth, the bird would have starved in a sea of slippery, high-speed prey. Nature rarely repeats a design this specific. We see the echoes of this engineering in the way modern raptors have traded heavy jaws for light. Keratinous beaks, the peregrine falcon, diving at 389 kilometers per hour, relies on a tiny bony tubercle in its nostril to keep its lungs from collapsing under the pressure. Pelagornis did something similar with its mouth. It traded the durability of ivory for the efficiency of bone. When you look at the jagged edge of that fossil, you aren't looking at a primitive ancestor. You are looking at a peak of evolution that existed long before humans ever looked at the sky and wondered how to reach it. There is a specific smell to a museum archive, a mix of dust, old foam, and the cold scent of stone. This is where the story of the pseudo-tooth bird is filed. It reminds us that the sky used to belong to giants that we can barely comprehend today. The 2014 skeletal analysis provided the final proof that size is not always a barrier to grace. By growing its weapons directly from its skeleton, Pelagornis sandersi bypassed the weight limits of the Miocene epoch. The solution was so elegant, it makes our modern aircraft look clumsy. It proved that, in the high-stakes game of survival, the lightest design often wins the longest hunt. What does this mean for the world outside the museum glass? The limits we think we understand about biology are often just temporary observations. We see a bird today and think we know what a bird can be. But the archive tells a different story. It tells us of a time when the horizon was filled with wings that spanned the width of a house. It tells us of a mouth that could snap shut like a biological trap without ever needing a dentist. The evidence is etched into the very bone of the South Carolina specimen. It is a record of a world that functioned on a scale we are only just beginning to calculate. The last piece of the puzzle was the wing itself. Researchers found that the bones were incredibly thin-walled, similar to the hollow spikes in the jaw. This theme of empty space providing strength is the defining characteristic of the species. It is why the bird could exist at all. If the bones had been solid, the bird would have crashed into the waves and never risen again. Instead, it stayed aloft for millions of years, a ghost of the open ocean that eventually vanished as the climate shifted and the seas changed. It left behind only these jagged, bony memories. The Deep Index logs this entry not as a monster, but as a miracle of structural integrity. We often look for the strange in the deep sea or the dark forests, but sometimes the most impossible biology is hiding in the light of the open sky. The pseudo-tooth bird represents a branch of the tree of life that reached for the sun and found a way to stay there. It reminds us that every feather, every talon, and every serrated beak is a piece of data in a much larger experiment. The experiment is still running. We are simply the ones lucky enough to read the results. What the index concludes: the Pelagornis sandersi utilized hollow bone protrusions to achieve apex predation at a scale that remains the absolute physical limit for avian flight. Subscribe for a new breakdown like this every day.